Hello and welcome to our next session of the Digital We Days. My name is Vivian Neuberger and I will moderate this webinar today. Today's topic is the future of power inductors, minimal losses and compact design. Also, I would like to welcome Theo Ritzmann. He is technical lead for power magnetics. From ferrite cores to modeled alloys, power inductors have come a long way. But how do modern designs balance losses and current capability? Let's explore the shift. Stage is yours.
Thank you very much. So, welcome everybody. Thanks for your participation today for my presentation. So let's jump directly to the agenda. So we will go now through, let's say, the history of power inductors. So first of all, we start in the early 20th century, where inductors were more or less mainly based on massive iron cores. Then we go to the 1970s, 1980s, and here came kind of a transition. So the inductors were then changing to ferrite-based versions. Around the 90s and 2000s, another step happened, and the inductors were then based on iron powders or alloy powders. And then for sure, also as the title of the presentation says, we will have a look on state-of-the-art present inductors and also what the future trends will hold for us. So, but let's say, as said, let's start in the early 20th century. So back in these days, the applications including power inductors were mainly in the low frequency range. So we are talking here about mains power supply or some filter chokes in the single-digit kilohertz range. And the inductors or transformers used for these kind of applications, they were based on really massive iron cores. So here on the right side, you can see how a product like this could have looked like. And besides many advantages, like many other advantages, the benefits of iron are that iron is a really high permeable material, and also the saturation flux density is really high. So with these products, you could achieve very high current capability and high inductance values. This was the main benefit. But there's also one major disadvantage of the iron, and this is that iron is electrically conductive. For these low frequency applications, it was actually not that big issue. But as soon as we come to higher frequencies, then we get some problems here. So what's actually the problem when we go for higher frequency? So here you can see a simplification of an inductor made out of a core and a coil. First of all, we have a current flow through the inductor. This is indicated by this red arrow here. This current will induce a magnetic field, a closed loop magnetic field following the core geometry. And if the current is changing, or if we have an alternating current, then this magnetic field will also create again currents, the so-called eddy currents, inside the material of our inductor. And these extra currents will cause, for sure, additional losses, additional heating of the product. We can also show this in another style. So here on the right-hand side, we have again our massive iron core, and right next to it, we have a simplification just showing the magnetic field and the eddy currents. So one first approach to reduce this amount of eddy currents was to use so-called laminated cores, so that you cut the core in single sheets, which are glued together. And this way, the eddy currents were not able to expand over the whole core volume. So at least in a 2D or two-dimensional way, you could limit these eddy currents. But let's continue with the 70s and 80s. So back in this time, or around this time, switch mode power supplies became more and more popular based on MOSFET switching technology. And why did they become popular? Because with these kind of topologies, you could enhance the efficiency of the whole converter extremely. But with this technology, also the switching frequency increased a lot. So we were talking here about double-digit or even triple-digit kilohertz range. And therefore, it was clear there was a new solution for power inductors needed for lower AC losses. And here, in a similar time, also a new revolution happened in the power inductor field, and these were the so-called ferrites, or ferrite-based power inductors. And they were actually not only used for the topic of the eddy currents, but also they were very popular as EMC inductors for this, as this topic became also more and more important. So let's have a look how a ferrite inductor looks like. So here you can see a typical cross-section of a ferrite inductor. In this example, it's our WE-PD series. And in the center, we have a so-called drum core, which is more or less a rod core with a top and a bottom plate. Then we have a shielding ring, also made out of ferrite, which improves the EMC behavior and also pushes the current capability. And then very importantly, between shielding ring and drum core, we have the so-called air gaps, which push also again the current capability of the product. And the composition of ferrite material is mainly iron oxide, and then it's mixed with, for example, nickel oxide and zinc oxide, which we normally call nickel-zinc ferrites, or with manganese oxide and zinc oxide, which we call manganese-zinc ferrites. And what is now the way to work against the eddy currents? The ferrites are more or less non-electrically conductive, or at least very less conductive. And therefore, the eddy currents don't even have a chance to expand or to be induced. The production process of ferrites is like following. So first of all, we are pressing the powder into a shape. Then we are going into an oven at high temperature, which is called sintering. And afterwards, we are grinding the ferrite in the desired shape. Some typically products made out of ferrite. So, for example, we can have pretty simple structures, just a drum core and a coil with either a THT or SMT termination, like our WE-TI series or our WE-PD2 series. We can have them with an additional shielding, like our WE-TPC or WE-PD series, as said, for the better EMC performance or the higher current capability. We can have some assembly types for pretty high current capability, like our WE-HCF and WE-HCFT series. Or there are also some innovative solutions existing, like our WE-LQS series, which is actually using an epoxy mixed with ferrite particles. And you apply this epoxy around the winding. So we can achieve with that a so-called semi-shielding effect. But what were the disadvantages of the ferrite-based inductors? So first of all, ferrite is temperature dependent. So this means as soon as we have a look on the saturation behavior of ferrite-based inductors, we can see that at higher temperatures, the product starts to saturate earlier. Then there's also the leakage. So at the air gap, the magnetic field is able to leave the component, and we could get some EMC issues. Also, the magnetic field can again induce eddy currents in our coil. This is the so-called fringing effect. And this will then additionally cause, again, losses and heating. And as a last topic, the switching frequencies are still increasing and increasing. So this means for these kind of applications, we need then again lower inductance values. But with the ferrite, we have here an issue, because when we want to have lower inductance values, we can only use a very low amount of turns. And then we are not using the space of the product efficiently anymore. Means we have in the end, for low inductance values, a poor power density. Due to these disadvantages, in the 90s and 2000s was then again a next step in the power inductors. And as said, frequency increased. So with the switch mode power supplies, we were going already in the range of triple-digit kilohertz, even up to megahertz range. And therefore, we needed lower inductance values, and for sure, they have to be very efficient, as switch mode power supplies have the target to be very efficient. The solution here was then to go more or less back to the basics, so using iron again, but this time not in form of a massive core, but in form of a powder. So you can see here on the right-hand side how this powder looked like. So we had these conductive iron particles. They were insulated by a layer and mixed with an epoxy. And then this whole powder is put into an oven, the epoxy liquefies, and after cooling we have a solid structure. This is the principle behind. The difference to the ferrite is now that due to this single particles, we have now not discrete air gaps anymore. We have a distributed air gap over the whole core. And this distributed air gap, as you can see on the bottom side with the eddy current explanation, is creating kind of a 3D lamination principle. And therefore the eddy currents are also then not that high anymore for these powders. Let's have a look again on the saturation behavior. What happens now with the powders? So here again, the ferrite, we have the temperature dependent curve. And then we have a look on the iron powder. So we can see with this material, the saturation behavior is now very stable. And also one benefit, this is due to this distributed air gap, is that we have this kind of soft saturation behavior. Means we have a constant inductance drop over the current. And this is also often a requirement from the market. Also, with the powder, we can produce now the low inductance values very efficiently because this distributed air gap is pushing our permeability now to a lower level. And this means now we can create low inductance values also again with a higher number of turns and make then more precise low inductance values. How do the products made out of this powder look like? So the first designs based on powder were more or less assembly types. So the powder was pressed in a core shape, and then the whole core was cured. And later these cores were then used for assembly by gluing, for example, or in this example, two core halves together. Even if there was a small air gap then between the cores, it was not really comparable to the ferrite inductor, so it has not that big influence on the performance. Then later there came also the so-called molding products. So now the powder was pressed around the coil and then cured after that. So not in an assembly process, but the curing happened then with the coil already inside. The huge benefit is that then we have a way better space utilization. But for sure, it has to be also considered that the inner construction and the inner materials also need to be able to handle the pressure and the temperature. The products, which are shown here, for example, on the left-hand side for the assembly type, is our WE-HCI. On the right-hand side, it's our WE-LHMI. Then, what happened regarding the materials? So, as said, the first designs were based on pure iron, but then there came further requirements from the market on efficiency, on current capability, and reliability. For example, iron is kind of sensitive to rust, therefore also you can work a little bit on these materials. Therefore, the alloys became more and more popular. So not the pure iron anymore, but an iron alloy with silicon, chromium, nickel, or aluminium became more and more popular. And there's actually also a difference between these pre-pressed cores for assembly and the molding materials regarding these materials. And next to the alloys themselves, also the powder structures changed in recent years, so that amorphous and nanocrystalline structures are becoming more and more popular. Here on the right-hand side, you can see some typical materials from WE side. So next to the ferrites like nickel zinc and a manganese zinc, we have here then the iron powder, but we have also some other powder materials named, which are mainly trademark names, like the hyperflux or the WE perm. Then, next to the materials, also we had some further optimizations, especially when it came to the molded inductors. So one change was, for example, the lead frames. Lead frame was always kind of occupying some space inside of the inductor, and therefore lead frameless designs became more and more popular, like our WE-XHMI, WE-PMCI, or WE-MAPI series. Then also one trend was that it was kind of a combination of assembly and molding became more popular. So that first of all, the coil was assembled on an inner core and then went later for the molding process. And then there happened also some production process adjustments to improve the performance even further, for example, molding under temperature. One very state-of-the-art product, very innovative product, which is combining many of these just mentioned trends, is the WE-MXGI product. What makes this product different, what does it make so outstanding, is that it has the lowest losses in the market in this package size. And this fits perfectly into the current trend of minimizing the losses. And also a special focus can be set here that the whole design is based on a round wire, what can be seen in the picture here. And this is actually really remarkable because the whole market is pushing into the direction of flat wires as the best choice for low losses. But this achievement was actually possible on a round wire solution. And how could this be achieved? So first of all, a very innovative nanocrystalline core material was used. Then also the already mentioned lead frameless designs. And as a result, we got this very high power density, huge current capability, and the ultra-low RDC and AC losses. And due to all these facts, this product is really beneficial for high switching frequency applications in the megahertz range. But when we come now to the future trends, for sure there are some limitations with the current technologies. So one thing is rough operating conditions. So we're talking here about high temperature or high voltage. What can happen at these conditions is the so-called percolation phenomenon. This was presented already yesterday by my colleague Efrain Bernal. And to say it in short words, it's the degradation of the material over time under high stress. Then we can also have some reliability issues. So due to the pressure in the molding process, there can happen some internal damage or cracks in the molding product. And then, like similar for the ferrites, we're coming to a point where the inductance values need to get lower and lower. And this means also with these materials, we need only a very less amount of turns. And therefore, we have again poor space utilization and not that good power density anymore for these very low values. And as a last thing, the trend of miniaturization, that when the structures become really, really small, it's getting difficult to mold them. So therefore, other technologies need to be considered. And all of these limitations were then triggering the future trends, which I will present to you now. For sure, it's not all the future trends going on currently in the market, it's just a selection. So first of all, I talked about percolation. And the reason for percolation is the degradation of the binding or insulation materials at the high temperature or high voltage. And nowadays, we tackle this problem by using materials which can take these rough conditions. But for example, like our WE MAPI HT series or WE LHMI HT series. But there are also other options, how the percolation can be reduced. So one approach is here that we could switch from organic binding and insulation materials to inorganic ones, because they don't show the percolation phenomenon. And here a solution could be to use now plastics instead of a binder material. So a material could look like on the right-hand side, so we would have then a mixture of metal powder with a polymer instead of a binder. And when we are talking about plastics, then for sure also the idea pops up that this can be there can be then also the potential of recycling. So either directly in the production process or also on customer side. Could be therefore an extra benefit with these kind of products. Also, one benefit when we are talking about plastics is that more or less the production processes of plastics could be then used to produce these kind of products. So here are two typical plastic production processes. And the benefit of these processes is that we could also cover this other limitation, which is the pressure topic, because we can get some cracks inside of the component or internal damage when the pressure is too high. And with the plastic processes, the pressure is pretty low. So therefore, we could get also rid of this problem. And when we think it even further, then we could also use materials which are actually pretty fragile as inner cores, for example, because as mentioned, the pressure is that low. And as a result, with this technology, then also probably some high-performing products could come out again. Second future trend I want to talk about is the very low inductance values. So here we are changing from wire-wound solutions to clip-based solutions. And this is actually nothing completely new. So there are already products like this existing, like the WE HCM series based on ferrite. So here we have two ferrite cores glued together. And typical for these kind of products is that they're highly customized. So you can see here some examples how the products could look like. Also worth to mention is that with the increasing requirements regarding switching frequency, also regarding temperature stability and soft saturation, here happens currently kind of a transition to also powder-based solutions instead of ferrite. So in which kind of applications are these products used? The main applications for clip inductors nowadays are the so-called multi-phase topologies. So these are converters where single converter phases are in parallel to handle high currents, for example, in server farms, in CPU applications or GPU applications. Then also these kind of products are used for the state-of-the-art TLVR application, which is also demanding highest currents. And here, mainly dual coil designs are very popular, like shown on the right-hand side. Same like for the single coil solutions, although these dual coil solutions are highly customized, because then they can also cover some extra challenges. For example, vertical power delivery is a thing which is currently a trend, or also to use the inductor additionally for heat transfer. And as said, as switching frequencies are increasing, these kind of clip-based power inductors could become more and more popular than also for, let's say, standard converter applications, not only multi-phase. But what's actually new now in the direction of the clip inductors next to TLVR topology? So as said, the trend is going from ferrite into the powder solutions. And for powder, we know we can either do the classical assembly or we can go for the molding process. But now there is a new technology, and it's called co-sintering, which is more or less the combination of both. So you can use the materials of the assembly process, but in form of a powder to actually make a molding process. But this is only applicable for clip inductors, to be said, because the materials then have to be cured at very high temperatures. And this can only a clip handle, because an enameled wire would immediately start to melt at these high temperatures. And then the third approach I want to talk about, the third future trend, are the so-called silicon-based power inductors. Silicon-based power inductors are produced in a similar way like semiconductors. So they are directly processed on a silicon substrate. So here on the right-hand side, you can see how a product like this could look like. And when we have a deeper look, it's a multi-layer construction in the end. So we have some copper layers connected via vias. These are then building the coil. And then we have some multi-layer magnetic material, which is actually also the very innovative thing here, is acting then as the core material. And in this example, we can then reach a height for this product of just 200 micrometers. And the products are not produced piece by piece in this case. They would be then produced on actually wafer level, so that we have thousands of pieces on one wafer, and then later they are cut into single inductors. Additional benefits for silicon-based products is the processability, because there are many, many options possible. So you can see here on the top side that we are going then from a pretty bulky discrete solution into a more and more integrated solution. So one step between would be kind of power modules, but we can go even then more integrated than that. And additional options for silicon-based products is, for example, that they can be ordered on wafer level with solar balls. So this means there would be a package-in-package integration possible at customer side. So this would be very beneficial for the customers in regards to building up fastly prototypes, and as it's good for easy PCB assembly. Also, the chips could be directly ordered as bare dies with copper pads, so for wire bonding integration, or they could be also actually directly embedded into the PCB design. And the flexible integration possibilities, they also allow for a chiplet approach. How do the applications for silicon-based products look like? So here is one example application. We have here a demonstrator board with a switching frequency of 20 megahertz and an output current of 400 milliamps. And the inductor for this application is a microtransformer, chip size 1210, inductance value 360 nanohenry. And you can see in the drawing that the height of the component is really just 200 micrometers. So we can see what kind of applications would be possible with this silicon-based technology. You can go for very fast switching applications or also applications which are extremely flat. So I hope I could show you a little bit what kind of future trends are still there, what could be coming in the future, what has happened in the last decades. And for sure, there will always be main drivers who are pushing the innovation and the future trends. So for example, as mentioned now many times, it's the miniaturization. This will go on and on. So there will always come more technologies, more solutions to make the whole designs and the products as small as possible. Then also the requirements regarding the harsh environment. So here mentioned temperature and voltage. The demands in that direction will also increase a lot in the future. Then we also have always the demand for as lowest losses as possible. Yeah, so the products we have these days are already very low loss, but the requirements regarding that will increase even further in future. And then also next to low losses, the components shall be also able to handle a lot of power. So this means we need very small components, almost no losses with a lot of current capability. This is where the trend is always going. So let's see what the future will bring to us. We can stay curious, and thank you very much for listening.
Yeah, thank you, Theo, for your interesting presentation. Information for you, the handout is now available and you can download it as well. And now we will start with our Q&A. Okay. So, first question. You mentioned ferrite-based inductor cores are less conductive. How are they treated when considering insulation and safety distances?
Yeah, so when we are considering isolation, so we have the isolation of the core itself. As mentioned, it can be that they are a little bit conductive, for example, for manganese zinc cores. Then we can apply some extra coating or some extra housing around the core to create this extra insulation. For isolation purposes, for sure, when we use them, for example, in transformers, we then have some creepage distances, we can have some extra enamel, some tapes. So there are many solutions already existing to reach this extra isolation between single windings.
Okay, thank you. Then next question. What parameters on an inductor datasheet can we expect to change, and what should we look for choosing the best inductor that has slow switching loss, percolation loss for a DC-DC converter?
Interesting question. So let's say for the datasheets, we are in that direction more or less limited. So in the datasheets, we are showing the basic parameters. So let's say for the first selection of an inductor, but when it comes really to finding the best match, to finding the product which has the best losses, then I can just recommend our Red Expert tool, because here we can simulate our whole application, and then we can get detailed information about our DC losses, about our AC losses. We can also get extra information about the temperature dependency of the product, which a datasheet cannot show. So therefore, highly recommended to use this tool when you want to really find the best match regarding the losses.
Okay, thank you. Then next question. Why are powders not that popular for clip-based inductors yet as for the wire-wound inductors?
Yeah, so in my opinion, the applications were not there yet for powder-based clip inductors. So because with powder, as mentioned already, due to the distributed air gap, the permeability is a lot lower compared to ferrite. And with powder, we could maybe produce products with 10, 20, 30 nanohenries, something like that, and the applications for that were not given yet. But now with the transition to TLVR and faster switching frequencies, we can see these applications coming more and more. Yeah, and therefore I also see that the powder materials are becoming more important for these kind of products.
Okay, thank you. Then next question. What happens to the inductor in a buck converter if more current is drawn than its maximum current during switching? And what are the consequences in the circuit? Will the inductor work for a while?
Yeah, it's actually depending also on the material and which kind of inductor. So when we are using a ferrite inductor, we have to be really careful regarding that, because we have this hard saturation effect. And if we are going too high in the current, then we have an immense inductance drop. And this can then in the end lead to a thermal runaway effect, because the whole component can heat up a lot. Then saturation starts even earlier for the ferrites, and then at some point we can destroy the component or the whole application. For powdered inductors, they can handle some higher current spikes. That's no issue. But for sure, if it's not a transient, if it's something happened frequently, then we have to also take care about the percolation phenomenon. Because when the temperature or the voltage also is too high at a long lifetime, then we can see these percolation effects, which in the end have a degradation, which have then, as a result, higher losses in the product.
Okay, thank you. Then next question. Do you have cores that are not affected by magnetic fields?
We have some products which have no magnetic cores. For example, air coils. We have also some ceramic inductors, but they are normally not used for power inductor applications. So mostly they are used for RF applications in the high frequency range, because for sure when the material is non-magnetic, then also the inductance values again for these products are pretty low.
Okay, thank you. And the last question, where can I find more detailed technical information about the microtransformer based on silicon?
Yeah, so there are already some papers, I think, published about the silicon-based product. Also some colleagues recently presented some information about silicon-based products. So if you're interested to get more information, then you can just get in contact with us and we can provide information to you.
Okay, thank you. Yeah, so now we are finished with our webinar, and very thank you for your attention, and I hope you enjoyed our webinar. Thank you to you, Theo. And yeah, if you are also interested in the topic power, we have the next days some other sessions. Yes, and you can register now then. Thank you and bye.
Thank you.